I'm not gonna have. I made this last night, so it's always gonna be I combined like 3 presentations.
So 10 o'clock.
Okay, let's go ahead and get started. Okay, so our first speaker for this afternoon session is Danny Jammooa. He's here at FRIB, and he'll talk about parametric matrix models for scientific computing.
Thanks for introducing me, Dean. As he said, I'll be talking about parametric matrix models for scientific computing.
Oh, yeah, I might need to click this slide just. Yeah.
So, at the beginning of the year, we put out a paper on the archive where we introduced parametric matrix models. We did some, fitting some ground state Hamiltonians, and then we did the Trotter problem in quantum computing, and some general machine learning like clustering, which Patrick will explain more about that. Mostly I'll be focusing on the Trotter problem and fitting two ground states of some Hamiltonian. So just a brief idea. So throughout history, scientists has been fitting all kinds of functions to data. Here I asked just ChatGPT to give me a list of functions. So just take a screenshot and put it there. And then at one point, we started fitting functions to neural nets, which are brain-inspired machine learning algorithms. Because we assume that our brains are pretty good at learning. So why not create a machine learning algorithm that does just as that? However, at one point, somehow we forgot about matrices, fitting matrices, especially since most of the problems in chemistry, biology, what we do here are eigenvalue problems, some observables, system of linear equations. But we just forgot about fitting that to data at one point. So that's what we went and did. We decided to build our machine learning model instead of based off the brain, but based off the physics. So a quick snippet on machine learning. Say you have an input parameter X, and then you have a model H that has model parameters W. We fit that to data by minimizing some loss functions. In neural nets, it's usually done by gradient descent. Then we have what we worked out, the parametric matrix models, which are based on solving matrix equations, and it combines elements of both RBMs and machine learning. The simplest one is this PMM, where it's linear in the input space, and what we fit to the data and what we minimize the loss function over is the eigenvalues of this Hamiltonian-like matrix. So as a quick motivation, in 2018, Dylan, one of Dean's students at that time, put out a paper on eigenvector continuation, which you all know, where given some high fidelity snapshots of the wave vectors as a function of coupling constant, you can form the norm matrix and then project your Hamiltonian to a lower dimensional subspace, and then solve that lower dimensional eigenvalue problem. And one could think that the final form of the eigenvector situation is of this form in a lower dimensional subspace. So we decided, what if we just start where eigenvector continuation ended and just learn this Hamiltonian in the lower dimensional subspace? So that's what we did. We chose a simple Hamiltonian PMM where the first term is diagonal matrix and the second term is symmetric matrix, and we fit its eigenvalue to data. So we tested both methods on this Hamiltonian that is a sum of non-interactive spins as a function of this coupling constant C. And we fit it on different system sizes of this Hamiltonian.
So to interrupt, but is this inherently a restriction that it has to be linear in C because the early applications of eigenvector just happen to be linear? Or is this more generally just pick this because it's the simplest thing you can start?
Yep, that was the simplest thing we started with.
But the PMM can handle any non-linear.
Exactly. And this was a simple case to test on this problem. So we tested on this problem, and as we see is after the 5 training points here in Diamond, the PMM was able to extrapolate pretty well after the last training point, where for any system size, where the eigenvector continuation starts failing as the system size increase, given the same 5 training points.
Is that just because the subspace has
smaller and smaller overlap with.
Either that, or maybe the eigenvectors are rotating as a function of C and where the eigenvalues are invariant. Could be both, or one of them. Now, this would have been, and then the rest is history, but this could have been a great origin story if it was true. That's not how it started, but we can go with it. So to test down a harder problem, we took the anharmonic Lipkin model from this paper where you have this anharmonic term alpha. In this figure, it's set to -0.6, and they varied it given this control parameter. So we took this Hamiltonian and we took the ground state and first excited state. And we fit a PMM and multi-layer perceptron on those two states. A few things to note is we chose the training points far away from the phase transition, which happens around 0.2. And we gave 2 validation points close to the phase transition. For the MLP, the validation points could have been used as training points because we used cross-validation when we're tuning the hyperparameters. And then we took this learned PMM on the first excited state and ground state to learn an order parameter. And then also we compared it with MLP. One thing you could do is you don't have to train these separately, the PMMs, you could train them at the same time. How we calculate this observable is once we trained we took the ground state of the learned PMM and learned it with another Hermitian matrix.
Can you remind me what's the phase transition? From what to what? From order to disorder, or what is the phase transition?
So I believe for this model from to the left of the phase transition, it's non-degenerate.
So this is the anharmonic?
Yeah.
Yeah, so for negative coupling, the Hamiltonian's unbounded below, because that's the coefficient of the x to the 4th term. And but we're truncating to some finite Hilbert space, so it's well defined, but it's just a dramatic cliff that you fall off.
That's if you vary the inharmonicity. This is varying the
Yeah,
control parameter.
yeah, so
sorry.
it's degenerate.
Disordered on the left, ordered on the right.
Yeah.
Okay, sorry.
And we see that by, baking in some of the physics, we were able to outperform an MLP, which is supposed to be a general function interpolator, especially in the region where we have no data. Another thing you could do with this learned PMM is extrapolate into the complex plane. And we can see, we can figure out where the branch point is, where the phase transition happens, and you can see we have good agreement. Again, this is in the case where we didn't give it to any trained data around the phase transition. So obviously, if you just want to extrapolate in the complex plane, maybe give it more data around that region. Now, I don't know how good of a salesman I am trying to sell you these eigenvalues, but don't take it from me. A team from Los Alamos and friends over there implemented our method on the Deuteron versus the RBM method they use in Gaussian process. And what we see for the ground state here, PDF, that past the last training point, PMM did a pretty good job at extrapolating and fitting those limit results. And on the right, we see that PMM also performed better in terms of speed and accuracy over the other 2 methods that were tested in this paper. If you have any question about this, probably just ask Pablo or Kyle, not me.
What's the y-axis on your right plot?
What's the delta?
Is a matrix of an error. In this case, is the error of the energy of the ground state.
Okay.
So think of vertical, how much error you're making, and horizontal is how fast you are. You want to be on the left downward curve.
Yeah, okay.
So that was the first problem we studied, and now I'll talk about the second problem, which has to do with quantum computing. Say you want to do some quantum simulation on a quantum computer, solving Schrodinger equation for a time-independent Hamiltonian. You could do a first order approximation, but that won't get you that far. Especially since most of our Hamiltonians that we study are K-local Hamiltonians. What I mean by that, there's 1-bond interactions, 2-bond interactions, so on, like the Hubbard or the Ising model. Even though the matrix dimensional is difficult to compute, it does act on a much smaller subsystem, and it's actually pretty straightforward to approximate on a quantum computer. there's only one problem, is if those scale-up Hamiltonians don't commute, you can't just write it out as a product of unitaries. So what we do is we use the Trotter formula that says if, say, your Hamiltonian is A plus B, you could write it as a product, but given this constant R goes to infinity. There's two approximations you could deal with. You could deal with the Trotter, which is the first order, which has error that scales delta t squared, and this is Suzuki Trotter, which scales delta t cubed. Then what you can do once you've done these approximations, you could implement them in your quantum circuit and have them act locally on the qubits. So to run through a quick example, I uploaded this slide recently and I deleted that, but it's fine. It's just because, you know, I had dt over here, but then delta t over here, so. But say you have a unitary that you want to run on a quantum computer for simulation time equals 1. Well, what you could do is, you know, you could implement the unitary 3 times in your circuit for delta t equals 0.33 and get the energy as a function of that t. You can do it 4 times, and then you do 5 insertions, and then so on. You could go to 0 to get rid of that delta t squared in the Trotter approximation. But one problem in quantum computers is we're currently in the NISQ era, which they're very noisy quantum computers. And say you have your error that comes from a quantum computer comes from theory error, which in this case it's your Trotter error. From state preparation and measurement. I won't talk about that too much in this talk. And then you have, you can't really see it, but it's epsilon to the L, the gate error. And basically is, yeah, sure, you could try and go to delta t equals 0, but what you'll get is a very deep circuit. And at that point, your qubits will decohere and you'll lose all information. So you want to find a good sweet spot where you don't want to be in that decoherent regime. So what you could do is calculate the energy as a function of dt and use some extrapolation function, exponential in this case, to go to dt equals 0. So I'll run through one quick example for the Heisenberg spin chain. Here we extended it to the next to nearest neighbor. Those are polyspins. What we could do is
Regarding that, so you just observe, it looks exponential and you fit it, or is that
Oh,
something reason to assume, like, what is the function?
I made
for?
this graph, so I knew it was an exponential.
Right, but you don't know necessarily the
No, you
actual
don't.
date, like, so what will you do in practice, like, how can this be safe?
Polynomial fits usually.
It's very different than
Or,
exponential, right?
yeah, I've seen papers that do exponential Richardson extrapolation polynomial fit.
But, it's like all over, like you just try everything.
Yeah. What I'll be discussing is, what you could do is, one of these students, Jacob, what he did is, calculated for, negative dt2 and then use polynomial to try to interpolate to 0.
Yeah.
So extrapolate through interpolation.
There's a general theory of what the error should be because the errors comes from commutators and nested commutators. So
Okay,
there's a
then-
polynomial expansion. Yeah.
I have another question. So instead of applying the value twice, why don't you say apply E, say A in the middle and then B delta tau divided by 2 on the right and B.
I didn't hear the first part.
Now you're doing E to the A delta T, E to the B delta T.
Correct.
And that gives you another delta tau squared.
Mhm.
And then you say, okay, well, if you can cut delta T in half and apply it 4 times. But like we know that if you did B delta T divided by 2, A delta T, B delta T divided by 2, you would make a delta T square. Is that more efficient because you have
You talking about with this Suzuki Trotter?
Yeah.
Yeah, you could obviously implement this, you get better error.
I think in practice, everybody does.
Yeah, as in practice, everyone does this, but just to get the idea of how PMM would work,
Okay.
we decided to go with Trotter. Obviously, it would not be hard to just make a PMM for this.
When you switch A and B here, does it give you any extra information for the same depth? Like, can you learn something about the error by just switching?
Switching A and B,
Yeah,
I do not know the answer to that.
And just pick up a minus sign in all your commutators. Should be the same. Or it's the same as if you took dt negative, right?
I mean, they're both approximations in the same order, but I wonder, like, if there's noise in your circuit and you do something that should be equivalent up to the same order, like, do you learn anything about the noise in that? My question.
You might know.
Yeah, so to some extent, the eigenvalues, I think, may remain the same, but they might be unitarily equivalent. You just put something on the ends, right? So from the eigenvalue point of view, there probably might not be any difference between switching to A and the B.
Right, I mean, that's, I
Yeah.
guess what I'm saying is there could be a strong point, like, it could help you by doing
Sure,
those two things that
sure.
should be equivalent, but then there's noise on top of that.
Yeah, if you can come up with a non-trivial constraint that the PMM needs to now satisfy, yeah, I agree.
So yeah. I'm gonna run through a quick problem. Where we have this Heisenberg spin chain that's extended to the next unit neighbor term. We decompose it into 5 terms, and so that's easier to implement on a quantum computer. We trotterize it. And then again, you start applying it to your circuit. So we thought, what if we just copy pasted it in a lower dimensional subspace? And just learn that. So this has 5 terms, so we'll write PMM as 5 terms, we trotterize it and fit its energy to the data that you get from a quantum computer using phase estimation or the Rho algorithm. So for this next nearest neighbor term, we took the training data far away from 0. And we compared it to a polynomial, and what we see is the PMN does a pretty good job at extrapolating to interpolation to 0. And on top of that, you could actually see in this instance that even though the training data was so far away, it will still be able to predict that there's some interaction between the states around 0, which is pretty fascinating. Next, we switched out that next to nearest neighbor term for this DM interaction, which is sigma x, sigma y, sigma y, sigma x. Here we scaled it up to 10 qubits because the previous problem was 8. And again, we took the training data far away from 0, and we asked PMM, polynomial, and MLP to fit to this data and extrapolate to 0.
So in the previous problem, what are the signs of J1 and J2? Can you have frustration in the system, or you not do the frustration?
Like,
Wait,
what did
J1 and
what did I exactly choose?
J1 and J2 opposite signs?
No, for this one, they weren't. I think it was B and J1 were equal to 1, and then J2 was 0.5, something like that.
There's nothing stopping us from doing different signs. There's nothing stopping us from doing different
I
signs.
think that would be cool. I mean,
Yeah.
created systems are very interesting.
So this is the other column, and then we decided to choose, this time around, we gave them a validation point, just to be consistent. For the MLP, again, the validation point could have been used as a training data because we use cross validations for the hyperparameter tuning, where for the PMM, those were the validation points. And what we see again, outperformed the polynomial and the MLP. And also, again, even past the training point, it was able to learn the structure. And what I wanted to basically talk about is show the LMG problem, what Pablo and Kyle showed with the Los Alamos, and what we are showing here is that if you build the physics into your machine learning model, you can expect some good interpolation, extrapolation in region where there is no data, especially far away from data. Lastly, I want to talk about current or future work that we're going to be working on. We will try to either create PMM specific to these problems or use existing ones if applicable. And then also study some different time evolution, time dependence, open process system, which we might do with Manuel. And maybe we see if we could say that we're learning something about the algebra. Quick exploratory work that we're working with Ryan on circuit compressing. This is very early. We don't even know if we're going to go this direction, but for example, he took the icing model and for 10 qubit and measured the magnetization as a function of time. Well, we took this and we compressed it to 3 qubits using PMM, which then we could probably put back into the quantum circuit, reducing the dimensionality. Another thing is, say you fit your PMM to some Hamiltonian, you have data on some observables. So say you have, you fit it to, one observable and the other, can we extrapolate in products of observables and say something, we've learned something about the algebra? These are my references.
Danny, very, very nice. Other questions? Yeah, Sebastian.
So when you go back, the first example, when you interpolated around zero was symmetric, and then the other one was not, it looks symmetric.
Yeah.
And then the next one is not symmetric anymore. Is that the choice of the model or?
Yes and no, this is actually technically not that symmetric, if you actually took this data and reflected it, it's not symmetric.
Okay.
And this one is, yes, probably because of this, term,
Yeah, that's what I figured. This is just more obvious.
Yes.
So to go back to the question I misanswered for Jorge, so that Patrick corrected me, so that was the anharmonic oscillator, right?
no.
Anharmonic
Okay,
Lipton.
anharmonic
That's
Lipton
why.
model, okay,
They,
yeah,
they are mapped to each other, but
yeah,
in this case, they're
Gotcha.
varying.
yeah, I'd forgotten which model that was.
So much.
Other question, yeah, Jane.
You touched very, at the end, a small blip of the Eisenhower. Can you say a little bit more about like, what dimension are you working with? How many,
This is the 10 qubit, so,
so is this like a transverse
1020,
field? Like
yes,
1D
yes,
Eisenhower?
transverse field. This is very early work.
Okay.
I just want to do, just put it up.
Other questions? Yeah, Sheila.
How do you dramatically increase the number of parameters
In, which one, just in general?
in the PMM?
You just increase the size of the matrix of the PMM.
But the size of the measure cannot be too big, right? Because otherwise calculation will be slowed down.
In terms of like training?
Yeah.
Yeah, the more parameters you have, the longer the training is gonna take. But you should, because we do gradient descent with Adam, you'll find a good solution at one point.
But you can also expand in more powers of your parameters.
Yeah, you can do feature engineering.
Yeah.
A follow-up question for that. So in terms of training cost, if you take PMM versus EC, say, for example, is it roughly the same or is? one more
Versus
expensive?
eigenvector continuation?
Yeah.
Eigenvector continuation is an offline, this is a projection method. There is no gradient descent or anything.
Right, but you compared the two at the very beginning.
Yeah,
Right?
because
So
they were-
because my impression is this is more expensive in terms of the
and
training.
in terms of the offline, yes.
Yeah.
Should,
So the outline is,
yeah, so
No,
I would
they're-
compare them
they're-
more to our neural net.
They're exactly the same. They're both in cube.
Yeah.
Per inference.
Yeah, but talking about times.
yeah, that's online, but I'm talking about the offline, like the training.
Yeah, so
Yeah, the offline, you should compare more to a neural net.
but
Instead
if
of,
you're doing a full cost, right, every time you do eigenvector continuation, you're doing another in cube step, whereas we only have. That's all during the offline phase and then during the online. phase.
The inference
So during
should be
the
the same.
inference, it's- No, it's, then it's small, there.
When you're comparing with the MLP, do you remember like what your MLP looked like? There's not just one.
I have it written somewhere,
Okay.
There was.
but it's
Check it
saved
out
on
in
the
a
file,
paper somewhere.
but I gave it a bunch of different layers. Shapes, hyperparameters, different activation functions, and I did grid search. So it's saved somewhere.
Are there other questions? Yeah, yeah.
Very briefly, in a scenario where you have level crossings, if you just train on, say, one region here, and then as you go in the parameters, and you have a level crossing, but you don't have any training points over here, do you recover?
So he's saying if the true data has level crossing,
Yeah, so like if, I think in one of these slides nearby with the LNG system, yeah, like here, if you only have training points just on the left of this point right there.
If you have it for the excited state, I think you get, but I guess the question that Cal is asking, if I only give the training points on the blue curve, but not on the excited state, neither on the.
That's hard, that's
That
hard.
you wanna get, we shouldn't be able to get.
If you trained it to exquisite accuracy, maybe you could, but it's hard.
I will bet that no way
Yeah.
on Earth, because the level crossing is just an artificial thing of how I paint my curves.
Mhm.
And the second part is the first curve coming down,
Mhm.
not a property of the lower curve. Is our intuition correct?
yes.
Are there other questions? If not, then let's thank Danny once again.
And my muscle memory, why would I? Just gonna-
Favorite noise, you have to do it.
Okay. All right, so we're going to continue the story, and Patrick Cook is also at effort here, and he'll be talking about parametric matrix models for general machine learning. Go ahead.
All right, propaganda part 2. So I'm gonna say, everybody just humor me and say that Danny did a great job, and now you're all convinced that PMMs are perfect for physics, or at least pretty good. But physics is not everything as much as my paycheck says it is. We care about other things also, and maybe fundamentally those things are also physics, maybe not. What we really want to know is, based on these results, do PMMs actually generalize to things that aren't just Hamiltonian dynamics or whatever else? Maybe I can recast problems that aren't physics into physics problems, or I can just brute force it and see if it works. The answer is yes, or else I wouldn't be standing. We can do this pretty well. But why do we care? So if you haven't been in the real world in the past year, you somehow don't know this, but now you know. General machine learning is like the most important thing it seems to be in terms of technology today. So, but also these models are getting larger and larger and larger. You may have seen like the most recent models from like OpenAI are approaching trillions of parameter things. And really, that's the only part that matters. If you had to just describe a model by one number, the one that matters the most is the number of parameters, because that's going to determine how much it costs. So in terms of like how much energy it takes to train, how many data points you need. So, how much information do you have to buy or legally acquire from the internet, and also where can I actually use this? So like my phone only has a 0.5 terabyte of storage, and that sounds like a lot, but ChatGPT probably takes more than that. Or at least the data that it used to train definitely takes more than that. And then also like real-time applications like self-driving cars or whatever else. If you have a massive model, the inference time could be several seconds. You probably used an LLM and you know that they're getting faster, but they're still relatively slow. It's faster to talk to a human. And so if we can reduce the number of parameters, we can basically improve every part of a machine learning model at once. I just said that. That's great. I also just said that. That's awesome. Okay, so the current solution is to throw money at it until it goes away. So this is a graph I stole, but I cited it, so it's not stealing. So time in years or whatever, and then on the y-axis we have the number of parameters and its log scale. And so right now we are in the just under 10 trillion parameter range. And so maybe somebody in here knows how many parameters the human brain has. No? Who wants to speak up? Anybody?
Neurons are synapses, which what do you count as?
Well, so parameters would be the connections, right? And how they interact. It's 100 trillion. So we're pretty much to 1/100th or maybe 1/10 of a brain. I don't think they're actually that smart yet, though. I don't think they're a 10th of a human. Maybe they're better than a 10th. It kind of depends what you think.
Depends on the human.
Depends on the human. That's right. So ideally, we'll want to bring this number down. And the claim is that artificial intelligence is better than actual intelligence. And so if that was the case, we would at least it would be an order of magnitude better in terms of parameters and performance. So we would have 10 trillion parameters and we would be a human brain, right? Just one order of magnitude. But of course, the claim is that AI is like infinitely better than. So we want to bring this number down without doing anything bad to the performance. Is that possible? Of course it is. So we're going to try it with PMMs, both as like a motivation for other people to get interested in it, and also to prove that the method is actually useful already. And it's always going to boil down to these two things. You're going to make a Hamiltonian. And of course, in the before case, it's kind of already given to us by physics, but now we're going to make our own. I put Hamiltonian in quotes because it's not a Hamiltonian, but we'll call it that. And we're going to use its eigensystem to do something. And I know that sounds really specific, but we'll go through a couple examples so that I hopefully will make you feel like, oh, I could kind of make my own to do whatever I want. So we'll imagine our Hamiltonian is a function of some features. So imagine it's an image. or like a vector of measurements or whatever else. And then we're gonna take its eigenvalue composition, so, V lambda, V dagger, Hermitian matrix, so we don't have to worry about all the complexities that might come with that. And then somehow we're gonna convert that to a vector or possibly just a scalar of outputs, which I'll call Z. So here's some examples. This is what Danny pretty much only used in the previous slide, which is just an affine thing. So as a real quick notational thing, I'm glad I underlined them because I can't tell that these are green. They're supposed to be green. But anyway, things that are underlined in green or just underlined, or I guess just green, whichever one you choose, are trainable. So these matrices, every parameter in them is a trainable parameter. Think about, the weights and biases in a neural net. We train them the same way with gradient descent. We take some derivatives. The only difference is it's way harder in terms of like the people who had to do the math to take those gradients. You're not them. I was them. It's done. So you don't have to worry about it. So other than that, it trains exactly like a neural net. So this is the pretty much the simplest one. We can do something more complicated. So we take some outer products, kind of inverse Rayleigh quotient looking things. Or perhaps if X itself is a matrix, our data is a matrix like an image, we could do something like this. And then how are we going to use its eigensystem? So again, the simplest thing is to just take the eigenvalues. So this is what Danny was doing. But we can do things that are much more powerful, like use the eigenvectors. So here I've introduced a new matrix, which we'll get to it a bit later, but it is also trainable. And you can see that this is just an expectation value. So you can think of this as kind of like learning an observable. And this is much more powerful. We can do some sillier things where we always use the ground state eigenvector, but we use a bunch of different observables for all of my different outputs. These are just some simple ideas. But how are we going to actually use these? Okay, so machine learning is unfortunately large, or maybe fortunately large. We're going to stick up here, top right. Now, it's very nice. People are, if anybody in here does like actual super duper ML neural net stuff, they don't even mad at me for saying this. But these are really all the same with a different loss function. Don't quote me on that. You might get beat up in an alley for saying that, but it really is the same. You just switch out your loss function and all of a sudden you've gone from classification and regression to clustering or dimensionality direction. Here you just don't have any data, so you make up your data as you go and you put it into a loss function that you also made up. But you can basically just use a neural net or whatever model for all three of these big branches and it all works. So, but we're gonna stick up here because it's simpler to at least to think through. But fundamentally nothing changes. All right, so the simplest possible thing in machine learning is regression. Everybody knows least squares and ridge regression probably in lasso and elastic net. So the idea is, can we make a Hamiltonian and use its eigensystem to do regression? We'll just do the simplest one. If I don't know where my data came from, I don't really have any reason to expect one thing or another thing is going to work better. So we'll just do the simplest thing. If it doesn't work out so well, maybe I need to do another sum where I do x squared with more training matrices, x cubed with more training. But we'll stick with this. And we'll actually see that this is more than good enough. We don't need to do that feature. We'll use its eigensystem in a very simple way, where I have a bunch of these matrices, again, these kinds of observables, and I'll use the eigenvectors. Now, you might notice that this is maybe discarding a lot of information because I have no cross terms in my eigenvectors, right? I could have VI, VJ, and there's definitely relations between eigenvectors. Of course, they're always orthonormal, but when I put this matrix in between, that product is not necessarily zero when the I is not equal to J. So,
Sorry,
yeah, you're fine.
I'm getting slightly lost. Can you go back? So X is the data you have, right?
Yeah,
And H naught and HI is what you want to learn.
that's right.
What are the underlying delta I's? That's something you have?
Something I'm going to learn as well. Anything underlined is something I'm going to learn.
Then what? So how do you tell it what to learn?
So you would
How do
also
you know
have,
what the
You would also-
ZIs, you have some training output.
yeah, you would also have some YIs in the regression. So all of these cases will have some labels Y. But they don't appear anywhere in the inference, of course. They're only in the loss function, which is completely separate from this. You just use MSE. It doesn't matter.
Okay, but in the end, you have like input and output, and all of the underlying things are just features of the particular model that you choose.
Yeah,
Correct? Sure. Next.
yeah. So input X, output Z, and then train to Y.
Thanks.
All right, so how can we use this eigensystem more effectively? Maybe taking some of these cross terms into account. I just said that. So here's one idea. So take the cross terms. So I have VI, VJ. Now I have a whole bunch of these matrices. So delta is a matrix. These are not indices into the matrix. It's a bunch of different matrices. Again, all of them are trainable. And so it depends on both I and J. So which eigenvector I'm dealing with, as well as K, which is gonna be unique to the output. So we can have completely decoupled output. You might immediately notice there's some issues here with it not being real valued. That's pretty bad. So you could just do that. That's also bad. Does anybody see what might be the problem with this?
How'd you get something negative?
Aha, that was quick. Now it's fine. Now it can be anything. Right, so this is our spectral norm. So this can't be larger than this, and so we divide by 2, and now it's got the full range. If you want to go to infinity, you can still learn that through its norm. It'll be fine. So
Why do you have to make it a real? It can be a complex number.
your output is not gonna.
You can think of real and imaginary.
You could do that. That's fine too. This is a bit more powerful for various reasons, especially in the gradient itself. Just picking up the real or the imaginary part is rough. But your loss function and your labels are always real. I don't know of any scenario in general machine learning, not in physics, where the labels of your data are complex. If you know one, I would love to see it. All right, so now I'm going to give these a proper name. Each of these deltas we'll call a decoder. I call them a decoder instead of an observable because they're not an observable. They're a decoder. We're not doing any physics here. I don't know why I work in this field. So let's just really simple 1D regression. It's not simple though, because these are discontinuous. And so let's do square wave, sawtooth wave, and this thing that Danny came up with that I disagree with fundamentally. So, we just kind of unleash somebody's laptop on these with a PMM of the exact form I just talked about, as well as every other machine learning thing I can get my hands on. Okay, so I try to keep these aligned. We have a curve error, just think of it as the mean squared error. It's basically the mean squared error on the x-axis and then each of the different methods. Can everybody read these fine? I've tried to make them as big as possible.
Yeah.
I can point to it. All right, the one that matters is in green because it's mine. And it's also pretty much the best, except for in one case where it's pretty much tied for maybe second or third, but it keeps up with the rest of these. Notice that this is not even remotely fair because Gaussian process, K neighbors, support vector machine, XGBoost, and random forest are offline. They always have access to all of the data. Every single data point that we use to train these with is stored within those models. The only two that aren't are the PMM and the multi-layer perceptron, which, and I know a lot of people have been saying that, it's just a simple deep neural net or shallow neural net possibly. There's nothing special about it. So you can just think of neural net. Yeah, only the PMM and the multi-layer perceptron only store their parameters. They don't store the training data. So they are usually, in terms of like raw storage space, much smaller. And also somehow more powerful. So we can actually see what some of these, just a select few, look like. So I picked PMM, K nearest neighbors, and multi-layer perceptron. And one thing I really want to highlight is these are discontinuous functions, all of them. And only the PMM can do a proper discontinuous output. Now, if you picked a very special activation function for the MLP, you could as well. But this is where we start to get into, really fine-tuning things by hand, which we're trying to avoid, right? Us as humans are biased and just wrong, but the computer is never wrong, unless you program it to be wrong, and then it's your fault, and it's the human's fault again. But we can be properly discontinuous because what's happening is with those decoders and those eigenvectors, you can have these level crossings where in the energies, it's completely continuous, but the eigenvectors will suddenly switch, which can cause this perfectly discontinuous output when you put it through the decoder. Okay, I moved a little fast. Everybody good?
Once in task here, you give it some set of points on the curve and you gotta fill it in, or?
That's right, yeah. So some of these points were training points and then it just tried its best to fill them.
Yeah, actually, about that question, do you have like the data points that you use to train? Because if you only gave like a finite amount of points in like the up and the down, I will expect that it could have happened that the curve was a smooth transition between them. How did the PMN got exactly where to do the drop?
Oh, yeah, so it's just a kind of uniformly randomly sampled, which will be training and validation. And you can actually see there are times where it doesn't get the chop right. Yeah, so this one was a bit late, right?
Yeah,
So it went past that. So yeah, I don't have them plotted because there's already too many points in that plot,
Okay.
but yeah, kind of
And I
a
should
uniform
expect that
random.
to happen, that
Yeah,
it's not going to nail it exactly unless it has a point in that boundary or close to that boundary.
Yeah, and that's exactly what happened. Yeah, perfect.
There's some relevance here to the fact that it's periodic, because if it were not periodic and imagine you give it training points, like, take the upper one and you only give it like the upper plateau, the lower plateau, but nothing beyond that, it would never be able to actually get the rest, right? Because
No, it's not gonna be able to extrapolate.
So my question is, did you tell it about the period or did you just uniformly give it a training point and then it learned how does it know where the discontinuous? How does it know that?
So yes, these are periodic functions, but this is just doing normal regression this is just a test function, so we're not treating it as a periodic function. We literally say that, X starts here and ends here, and that's it.
Where about the training? Because I'm fascinated by the fact that it knows the discontinuities.
The
but we
training
don't-
points are kind of uniformly distributed over.
How near the discontinuous points are the
You
training?
can see some,
We can talk more later. I don't have them on this graph.
Right.
I can't, especially since I purposefully omitted the x-axis because it's meaningless here. Yeah, I can't give you like a number.
well, you see
I
that.
can do this though.
Yeah, qualitatively, I'm asking, like, do you have training at the discontinuity points?
Yeah, none of them were exactly on the discontinuity, but they're,
Pretty cool.
just because of random sampling, they happen to be.
So just a question that, so when you train a GP, if you put too many training points inside a correlation length, there's.
Yeah.
Computational problems, if no condition, do you have anything like that or?
I wish I had Danny's plot, but it's physics related on here, so I'm not allowed to use that. But in the Pablo Kyle at Los Alamos paper, that exact problem happens. Where they have two training points, which I'm not sure if they're exactly degenerate, but they appear to be, they're qualitatively degenerate. Their GP fails at that point and we have no problems. So no, we don't have that problem.
Okay, that's big.
Yeah, sorry, just want to understand a little better.
Hmm?
Previously you showed h of x.
I wanna go back, forward, I'm spoiling everything. Really pretend I didn't see
Yeah,
that.
so here, xi is this I, like say, a points on the x-axis or?
No, it's features. So in this case, we're doing 1D, so there's only one I.
Right, so in this case, you only have one hi, say.
That's right.
And then what's the size of this h to get the precision that you?
Danny,
Hmm?
do you remember?
What?
You sent me this data.
Yeah,
You
I
did
didn't
not
get the
pay
question.
attention.
Or the
How big is the PMA in the
Oh,
body?
6,
6 by 6, there you go.
6 by 6.
and I use I plus 3 for the,
Yeah, so we keep 3 eigenvectors around, so we do, ij goes up to 3. Or rather, I goes up to j goes up to 3.
Okay, and do you remember the dimension of the feed-forward neural network? Like-
Yeah.
I just saved them to a file. I didn't read it.
Yeah, okay, but like.
I gave it a big list.
Definitely several hundred parameters.
I made sure
if
to
not-
go close to what the PMM was and a little bit larger. In terms of
We'll get to more direct comparisons of parameters in just a minute with problems that are less contrived. In fact, I would not say, or I would say they're not contrived. All right, 2D, it's one more than 1D. Did you have a question?
I can save it.
No, you're fine. I'd rather do.
Okay, I was just wondering, what is the biggest Hamiltonian that you've trained? Because you have to solve the exact eigenvalue problem.
Yeah,
right?
in practice, we never need anything close to like 1,000 by 1,000, which is easily
Oh, yeah, but what
infinitely
is
diagonalizable.
it 10, 50?
I've used 20s to do
20?
things,
Okay.
yeah, with no issues. When we get to some more problems here, it becomes less about this Hamiltonian size and more about some other things.
Okay.
So what is the meaning of this number, this dimension basically of this Hamiltonian? Because you say 6 by 6, but what is the meaning of this number? Does it capture?
Do you mean like its interpretability
6 by
and
6 in this case, what is the meaning of this number? Why not 12 or 20?
same, so recast your problem in terms of a neural net. Why not 10 million layers instead of 10,000? The reason why is you do a few and you pick the best on the validation set. That's what we do as well.
So there is no guiding principle behind this.
There need not
This
be,
number except trial and error.
For the physics problems, there is,
Yeah.
but not here.
but not.
Yeah, we'll treat it as a hyperparameter, and that's something that is.
What is nice is, while I don't want to get too much into this with this talk, but well, core philosophy is to try to get rid of any hyperparameters or the ones that we have be much easier to deal with or physically motivated. With the PMM, that size is, what's nice about it is with a neural net, you have both the width and the depth, which are completely separate.
Because let's say you increase the complexity of the data.
Mhm.
That's basically what you're doing as you go down here. Will you need more and more,
In general,
Yeah.
same thing with the neural net. All right. Okay, 2D. Now, these are less contrived because other people contrived them for us. So this is literally a function that was created to be difficult to deal with. Those of you who know how to pronounce foreign names would know how to pronounce this. Can somebody tell me, is it Frankie or Franke? No one?
Franca.
Franca?
Probably.
Let's go with that.
Okay, so then we do our thing again, and we'll try to get through this a bit faster. Same story again. We do best. And this is also, giving all the methods, basically is as much advantage as they can have. So we rescale the data properly, you know, hyperparameter tuning where on the methods that we can, all sorts of stuff like that. Another function, this is also contrived because nobody put their name on it unless it was Flip that made it. Literally almost exactly the same graph. I swear it's a different one though, but it happens to look almost identical. I triple checked, the numbers aren't the same. Another function with a name this time. It's supposed to look a bit Gaussian, but it's sharp in the middle. This is the function that gives you the Runge oscillations, Runge phenomena, Runge phenomena. Pablo?
Just to have an idea, Patrick, how many data points are you putting in there, and more or less where they are? Just to have an order of magnitude in my head.
It was 400 data points and I've sampled randomly.
Uniformly sampled.
Train.
At this point, many of the things you do seem like magic, so I was expecting like 3 points in the corners.
No, it's not. I wish. Yeah. So, yeah, a lot of, we are pretty good with sparse data. Yeah, that's good. Okay. Now let's do something that's actually real. Image classification. Now it looks like machine learning. Everything else kind of just looked like scientific computing part 2. But now it's computer vision is very machine learning. It's kind of magic. It's definitely not physics, probably. So let's make a Hamiltonian and do the other thing. I have no idea where to start with this one, so we'll come back to that. This one's easy. We just do what we did before because it's really powerful. Why wouldn't I? But let's think about this. So now my input is no longer 1D or 2D. It's not a feature vector. It's this image, which is not a symmetric matrix. It's not even really a matrix when you think about it. So what can we do to make this into something that's more natural for PMMs while also being natural for images? So those of you familiar with feed-forward neural nets or dense neural nets, they just vectorize it. They take each row and they strip it down and make it into a giant column. With convolutional neural nets, they keep that as a matrix and then they put a little window over a bunch of chunks and apply like tensor products to that, some of them. But both of those kind of destroy some locality information. So the idea is just take the correlate, treat the image as a bunch of independent samples on the rows and then on the columns. So basically just undo the image idea and then do the correlations of the different rows and the different columns. And then if you rotate the image slightly, and you do that again, you start to see this pattern emerge where all of my zeros kind of have this cross shape and all of my 7s have this box shape, and so on. And of course, as humans, it's not exactly easy to look at this and say what number it was, but the machine will. That's fine. Now, the problem is this is expensive, right? If you think about doing correlations, there's a lot of work to be done. Amazingly, the square, so let's just look at the window here that I have highlighted. This is the correlation of the rows. If I just square that window, and I put a dagger here, but it's a real value, so it's a transpose, has pretty much the same idea going. Yes, it's different. Oops. Yes, it's different. But it's really not. It also contains pretty much all the same structure. If I do some normalization to make things nice, and I enforce the diagonal to be all 1s, then it really does basically contain the exact information we want. This is not true in general, but for images and this sorts of things, this is great. All right.
So here, the image is X, and you're squaring that.
Yeah, the big X, yeah, okay, that's right. All right, so how do we make our Hamiltonian? So I'm gonna do this. So I'll divide it into blocks like those windows, especially one window. Just pick a few. Take the blocks out, do the approximate row and column wise correlations. I put proportional-ish here because I do that normalization and I enforce the diagonal to be 1, just matrix stuff. Now we're gonna get into the weeds. So again, underline means I'm gonna learn these parameters. Okay. Now these are the same on either side, K, L, and L. So it's not 4 matrices here, just 2. And they're just complex rectangular matrices. There's no hermeticity requirement here, no real requirement, nothing like that. And you can see that when I do this, right, so I'm going to sum over all of my blocks. That's the I here. So I took those windows of my image, sum over all my blocks, and apply K and L to K to the rows, L to the columns. Column wise and row wise squares, I should say. Of course, you need to define K and L such that their sum is compatible. That's fine. Notice that the rows and column blocks can be different shapes. So you can have rectangular windows, which is nice, because then the interior dimension or the right-hand dimension of K and L will just be different. And this whole sum and well, each product ends up being permission, which is nice because it makes training nice. To do that, we get M. Okay, now I'm going to introduce another one called these the discriminators. So these, again, just another matrix. These are, again, just rectangular complex. They don't need to have any sort of nice form to them. And C here is going to denote my output index, since I've already used I and J, and well, I haven't used any of those yet, but I will use IJ, so that's good. So C will be my output coordinate, just like the ZIs from before. Now let's have a bias matrix here. So now we have our Hamiltonians. Now we have more than one Hamiltonian. We have one Hamiltonian for each output. And we'll do our diagonalization. So for each output, if I'm outputting, we're going to do image classification, and I'm doing digits of 10 outputs. So for each of those outputs, I have another Hamiltonian. These are very small. These are like 4x4, 5x5. So very cheap. I do my decoder formalism. Same thing as before. And the final step, because I want to do classification, is I put it through the softmax function, which just converts everything from numbers to probabilities. All right, the weeds have been trimmed. Everybody good? Okay, now the propaganda really starts. Oh, Padula? How do I come up with that structure? So first off, the blocks, doing the blocks and doing the row correlations, I think are relatively, row and column correlations are relatively self-explanatory. The blocks come from the idea of convolutional neural nets. We just look at a bunch of windows, right? The row and column-wise correlations come from how can I take an image, which is a matrix, but it's not. It doesn't have any idea of a matrix. It just happens to be an array of numbers. It's 2D. How do I make that into a form where it actually has properties of a matrix? The diagonal is special. The off-diagonal is anti-special. All these other things. And so you can think about doing an SVD, right? Or an actual eigenvalue decomposition. You could square the matrix to ensure that it's symmetric. You do your eigenvalue decomposition. You could start to get out principal components again. Now, when you do that, you realize you missed some information. And so you want to do row and column wise things. And you kind of work through these things where it's like, how can I make this into a matrix? Right. And for images, it's relatively natural. For other things, it might be worse, but that's why we have the old affine PMM. If you didn't do this, you didn't do this part, and instead you just did H0 plus XI, HI, it's not going to be as efficient, but it works. In the original paper, which I don't recommend anybody read because it's so old at this point, we do that and it works. So you can do the bad thing, you can do the good.
I'm not mistaken, something like JPEG compression does something very similar, right? You also take an image and you represent it through some Fourier mode composition. So how does that relate to what you're doing?
It doesn't, because we don't take the eigenvalue composition of the image. We do all this stuff to it first. You can imagine doing that. You can imagine just giving the principal components of the image to this method. And again, now you're just doing the same machine learning problem with different features.
So it's just you're throwing away something before by doing that thing. Then.
Yeah. We just make sure we don't throw anything away until it thinks it's necessary to throw it away.
So in the original paper, you had say 64 Hamiltonians in a sense.
In the original paper, I had 64.
Like if your image was 8x8, then you made it 60 vector, which is 64. Like,
Okay.
And then you had 64 features, so you would have a sum of the I from 1 to 64.
Yes, that'd be right. Yeah. And these are pretty small Hamiltonians.
Sure.
Yeah.
And that would somehow work. I mean, that would work.
It does. Yeah. That's obviously the less efficient way.
Sure, but
So you can also think of these if you want a more interpretable way. So the K's and L's can be compressors. Usually their output dimension is smaller than the input dimension. So it takes a window that's like this, applies its transform to either side, and it gives you back a matrix that's like this. The discriminators can do the same thing. Now the discriminator has a nice name because it tells you what it does. It says, take this encoding and then split it into a slightly different projection for each class I care about, for each output I care about. But it can also do the same thing. It can also be a compressor at the same time. There's lots of different ways to think about this. These are of course linear compressors, but we don't want to go into neural net territory because we don't need to. All right, now actual propaganda. So this is probably the most common computer vision task. Is anybody not familiar with MNIST digits? Well, okay. It's a bunch of digits, and we want to look at an image and tell you what it is. So current state of the art, according to papers published, is this. So deep neural net 2, which uses trainable activation functions. I won't get into the weeds. It's a very impressive method. It uses this many parameters and it trains them and gets that score on the test set that it had never seen before. We do our magic that I just showed, and we do that. So this is now, I claim, out of all of the papers I've been able to find and aggregate papers and all these things, this is the best of, whoops, don't look at that. But this is the best out of everything that's published and peer reviewed and whatnot. So that's good. A bit of a disclaimer. Notice that I've intentionally beaten the number of parameters by more than half. That's because I'm counting the number of complex values, which are 2 floating point, but 2 real values. So depending on if you're thinking about computational scaling or storage, and depending on what kind of, float representation you use, you might want to put me at the disadvantage and multiply this by 2, and we still win, so it's fine. Here's just an idea of what this kind of looks like. So I'm going to take each class and give the true class value just a point in space. And then I'm going to take the linear combination of whatever the predicted probabilities are for each, image I put through. And I'm going to project it onto these. It's a weighted sum. And so you can see it really is learning like the idea of a number, because 4 and 9 get a bit confused because they kind of look similar, especially in the training data where there's more data overall. You see like numbers kind of get confused for each other more so than unlike numbers. It gets a bit more obvious in the next one. I don't want to go into what's the difference between a shirt and a t-shirt, but just know that somebody with a definitely important job labeled these properly. So same song and dance. They get this with that many things. We don't beat them. Well, pretty good, especially for 2 grad students, 1.5 grads with not a lot of time and a model that's based on physics. It's pretty good. And maybe you could do better, maybe. And now you could really see this idea that it is learning relations, right? Shoe and boot, sandal and shoe and boot, coat and dress and shirt and what if I just did this for my entire talk? I just said.
Sorry, did you just, too fast, explain the diagram again?
Yeah, okay, so each class, so
Yeah.
every image that is a pant.
Yeah.
Singular pant, would, if classified exactly correctly, right, the probabilities are 0, 0, 0, 1, would end up here. Similarly for t-shirt. So now what I do is I put my image through, I get a bunch of probabilities. The point that it maps to is probability pant times pant XY plus probability t-shirt. You get the point. So that's where these end up. Does that make?
So something that is in between shirt and t-shirt is something that got classified kind of half and
50%,
half probability.
yeah, 50% of it, yeah.
This is partly hard because this is very low resolution data.
And I'll tell you what, if it was 4K 1080p and I was holding it in my hand, I don't think I could tell you the difference between shirt and t-shirt. But I guess I'm not outfashioned instead, that's why I'm standing here.
That's a popular copy of shirt.
Well, then how do you do some of these other ones? Anyway, somebody else have a quick,
Yeah, so, how do you, set your parameter number? You just set the number and get to the rate.
I don't set the number of parameters, so it comes from the images themselves, right? They have some shape, the number of windows I choose, how many windows I choose, the size of the discriminators and the compressors, how many eigenvalues I keep, eigenvectors I keep. Again, these are same thing with a neural net where you get to pick some sizes. The nice thing is that we know we don't have to search that many sizes. We also have some constraints on like the number of eigenvectors you keep can't be larger than the matrix you diagonalize. So we have some bounds on these things. So the number, or rather the space of hyperparameters to search is very small compared to a lot of deep neural nets.
Is the model you're comparing to the best performing with a certain efficiency?
It's highest efficiency. Now, of course, how do you define that, right? Because I can't just divide a percentage by a number. That's silly. So really what I did is I found papers that had the absolute lowest number of parameters with a what I would call respectable performance.
Does the PMM scale pretty well? I mean, if you let yourself be inefficient, you go bigger and bigger.
Yes and no. Why do I keep
You need a cat plot.
I do want a cat plot. This summation here is actually quite restrictive. When we do a really long sum, we kind of mix too many signals together. There are ideas forward. I think I have that on my last slide. Daniel, you gotta talk to me later and not ask now, because I'm out of time. Let's get to the last one. Okay, now we just do the thing again, but harder now with a bunch of classes. So I only showed 10 classes before. This is 47. You might think it should be more than that because uppercase, lowercase plus 10 is not 47, but they've grouped some together. Like letters that should basically look the same, uppercase and lowercase, are in the same class, except for some reason F isn't, and these two look, I don't understand, and I and L, it doesn't matter. We do our thing. I don't have a method to compare to because all of the ones are massive, huge models that, basically at 99% we don't. But, impressively, with just 5,567 parameters, again, complex numbers, we get 80-ish% accuracy, which is for this set actually very good. Just trust you. Okay. I'm done, I'm out of time, you can read, okay. Okay, we're done.
That's great. Yeah, more questions. Ellie.
Yeah, that's great, thank you. Actually, can you do multiple layers in a sense that use the output Y as input X, yes, and then try and see what?
Absolutely, we can. We haven't found that to be useful, but
Oh,
we can do it.
but it's not useful in a sense. It's better to have a bigger matrix rather than having a small matrix and two iterations. So.
Usually, yes. Yeah, I'm sure there's a contrived example where it's better the other way around.
Yeah, okay.
You can also do, especially if you're considering doing like the affine one, H naught
Yeah.
plus, you can do like a perturbation analysis, like perturbation theory approach to it and see that it's really not any different than just doing more. But
Right, I was thinking more about a fine transformation, which
Yeah.
change a lot, and then you want to iterate the matrix H in a sense, like.
so, yeah, there's nothing stopping us from doing that. There is some practical reasons why we might not want to. So you're familiar with the vanishing gradient problem. One of the reasons why this is probably so powerful is we only have 2 layers. And so there is no such thing as a vanishing gradient here. Somebody else had something?
Thank you.
Nigel?
Have you tried to explore the relation between your success, the probability of the success and the parameter number? For example.
Yes, sorry. So size of the model versus accuracy?
Yes.
Absolutely. So we have basically the same thing that all models have, which is diminishing returns, right? So it gets better, eventually it kind of flattens out, either due to the fact that the data is noisy enough that you really can't do better. Can you tell these two apart?
I know.
Right, come on. So yeah, we do better. We don't scale like transformer networks, the thing that's currently ruling our lives and commanding $1 trillion a year. Those are very impressive. But there's ongoing work that I think can improve our scaling quite a bit.
Yeah, maybe if you want to compare with your PMM and other models, you can show that kind of curve. So that would be.
Absolutely.
Yes, Simon.
Yeah, so one thing though that's kind of interesting is that what in the terms of analyzing like the neural network field theory stuff that I'm doing is that there's evidence that they have that as you increase the number of parameters in the neural networks, you're going to eventually, you're going to continue to the point where you're overfitting, but eventually there's a regime that you can cross actually where it starts to improve as you add more and more parameters. It's no longer overfitting because you switch degrees of freedom from the individual parameters to like the couplings that I'm interested in. So this is less of a question and more of just, I want to talk to you.
Well, that's the point of the symposium.
Yeah,
You're not here to
So to say it
listen.
another way, the complexity, the measure of complexity is not the number of parameters in those networks.
Okay.
So yeah, I like that. And it's just, this is really interesting.
And now it's like really like a physics kind of model. You were like, I'm gonna mush some field theory into a neural net. This is like, you can just put field theory on this, it's fine.
Yeah.
Yeah, but
Is there any way to reduce even further the number of parameters by factorizing some of your matrices as tensor products?
Go ahead.
Yes, that's the end of that question. We did that in the archive paper.
Yeah.
In our final unsupervised image clustering.
Because it's likely that at some point, many of these parameters are redundant in some way.
Absolutely there.
Yeah, Pablo.
Yeah, I was going to comment on that. You know how one thing that you could do with neural networks is start dropping weights. It's something like that, in where once you have trained your thing, you can start messing with it in a way that you get rid of redundancy.
So sparsity promotion is significantly less useful here, right? If you think about, we're diagonalizing Hamiltonians that are 7 by 7. Is a sparse 7 by 7 really worth it?
No. But yeah, of course, I agree. But you have 2000 and something parameters that came from many 7 by 7s, and that's what I'm thinking.
The tensor network idea is doing that, but in a, I want to say, a smarter way, just because of the form we have.
Okay.
Right? Because we want to keep those individual matrices dense. We want all of their parameters to matter in their eigenvalue composition, but it's possible that 2 of them can correlate very strongly, and that's where the tensor network would.
Okay, let's thank Patrick once again.
Sorry, I ate into your time, Pablo.
No.
Also
No,
my fault.
okay.
We'll have all of this.
If you don't mind downloading it, because
You uploaded, you mean you?
I did it like half an hour ago.
Yeah. go.
But download it because the Google Drive thingy doesn't work well.
Yeah. Pablo equations.
Yes. Like 100 megabytes.
Or minus.
Yeah.
Love that picture. I don't think I've seen this yet.
This is the entry picture of all my talks.
Maybe I just never pay attention to your talks.
I'm worried that
Everything's okay?
the fonts are just weird, but that's.
Okay. All right, so,
Draw that or generate?
Yeah, I made it.
all right, our next speaker is Pablo Giuliani. Here at FRIB, and he'll talk about beyond projections, learning equations from data.
Thank you. Before starting, I just want to say, Patrick, I was just an outstanding talk. Same with you, Danny. I don't see you. But
He doesn't.
okay, anyway, I am truly impressed, really. The things that is incredible. I am very much waiting for you to put it on the archive with the upgraded version so I can read. I don't think I'm going to take the entire half hours. I have many things that I want to comment. There is a point in where I'm going to once again show how things that I thought we were coming up with existed in the literature. There is some overlap to the things that we were pursuing and PMMs, but nothing that I have read has any resemble to the things that you're doing. I really think that you are inventing something and it's wonderful. So I'm very excited. So after those talks, especially Patrick's last talk that was very big, broad view machine learning in general, I think it's going to be a bit harder to keep attention span on something more scoped towards physics. So I'm going to bring us back to, I'm just going to be thinking on how to build better reduced order models for physics problems. How much this is applicable to machine learning in general, that's not my problem, that's Patrick's problem, and we already did very well. So this is the outline of my talk, and in an incredible change of events, I'm going to start with my conclusions, and I'm going to repeat them at the very end. My conclusions that I'm sharing with you today are three. My first conclusion is that I really believe that we are at a point in where we can streamline the creation of reduced order models for nuclear physics, and I swear I came up with the word before realizing that it's a nice place to work with our collaboration. But I really feel that we are in that situation. I think that a key to do that is going to be mastering this idea of learning equations from data instead of having to go through a lot of hardships to create those equations. And I'm going to show examples of all the pain. Vitek usually says how it's not necessarily nice to give a talk and show all the pain that we went through to get the result. But in this particular case, I think it's relevant so that we as a community can appreciate why this could be a good thing to invest in. My third point is that I believe that we should really thermalize with the literature out there on people from the model reduction community that has been doing similar things for the last 10 years. Okay, very quickly how it works. I probably everybody in this room has seen these slides at some point, so I'm going to go quickly through them, but it's important to at least have a context on what we're going to discuss after. How the model reduction that we have been playing with works in my mind. I have a very complicated set of equations. I'm going to write that as an operator f parameterized by parameters alpha on a set of wave functions or whatever you're using equals 0. I'm trying to solve to find the roots of these equations. I have some controlling parameters, and as Daniel in the morning illustrated, I have some calculation software was written by a grad student thousands of years ago. If you were to open it, it's playing with a lot of high dimensional structures, wave functions in this case. And then out of these controlling parameters is giving me what I'm after physics-wise. And what we're trying to do is, can I bypass that? Can I go in a quicker route that allows me to arrive at a very similar answer using less amount of degrees of freedom?
And in this talk and in general, I like to think of the comparison between these methods. At the end of the day, a finite element method is a method, it's a calculation method. We like to think of this in terms of a cat plot, a computational accuracy versus time plot, that is going to show the different trade-offs between accuracy and speed of the different approaches that you use. So I have shown this slide many, many times in where we are thinking of replacing these models or these posterior distributions with these emulated versions, and there are many choices that you can make. For this talk, I want to think in two ways. You need to find good reduced coordinates. Probably all of you have heard me the example of the brick. Good reduced coordinates for the bricks are not the position of the atoms, are, for example, translations and rotations, degrees of freedom. And you need to find equations for those reduced coordinates and how they evolve in time, parameters, whatever. And there's an example with the harmonic oscillator, because we're going to use this for the rest of the slide. I have my operator, Hamiltonian, acting on phi. My parameter alpha is the trapping strength. If I were to solve this in a finite element method approach, I discretize my space, and now my wave function phi is a list of many, many numbers. For example, 300. So if I paint that in a 300-dimensional space, it's a vector. If I now go and solve the problem for many different values of alpha, I obtain many vectors in that place. And if I do this continuously, I will get what we call the manifold, the solution manifold, which is that trajectory of the vector as you're changing the parameter. We're trying to learn that. And many of these linear embedding techniques, like the reduced basis method, what they're trying to do is to find a plane linear space in where I'm going to embed the trajectory of that manifold. The idea is that in here, if you limit this for a real, like a plane, that is going to have coordinates for phi1 and phi2, I will explain that in a second. I'm reducing my problem from dimension, let's say 300 to dimension 2, and that's why this thing is very easy. So for the quantum harmonic oscillator, the reduced basis tells you just expand this into two bases that we usually like to obtain from a proper orthogonal decomposition or a principal component analysis or a singular value decomposition. And the reason is what I wrote on the board. So you have a bunch of solutions, you extract what are the most active components as you were varying your parameter. And then you rewrite your Hamiltonian problem as f of this thing equals 0. You do a Galerkin projection, which I realize I don't have to share today. I'm so sorry. But once you do this, for this specific example, since I have two coefficients, I'm going to end up with two equations. Once I make my two Galerkin projections on my operators. Two coefficients, two equations, one extra for the eigenvalue, but doesn't matter. And then I'm fantastic. So this is a summary of how it works for the harmonic oscillator. Two steps. Find good reduced coordinates, in this case, the amplitudes of my reduced bases. Find equations for them. In this case, projecting on Galerkin, I'm going to obtain a system that looks like this. Small matrix times coefficients equals lambda hat times coefficients. Fantastic.
In the previous equation,
Please.
I mean, there is something else that you have to supply, right? Because in principle, you can get A1, A2 equals 0 as the only solution, right? Then you have to supply something else.
Yes, the normalization. That's why I said the lambda, you're right, Jorge. There's three equations. There is the equation that I want this thing to be normalized to 1. And I have one extra unknown, which is the eigenvalue of, but lambda, it is. Thank you for pointing that out. Okay, as an animation, this is how it looks. This is my vector moving in my high dimensional space. This is my solution changing as I change the parameter. And these are the reduced bases multiplied by their appropriate coefficients. And that is how this looks. Now, if you want to know if this is going to work for your problem, we talk about the PCA doctor, and she will come to your problem and realize how the singular values of your manifold are decaying. If they're decaying exponentially, you're good to go and you can apply this. Okay, that was my introduction. Now, let me talk to you about the gain and the pain. If there is no pain, there is no gain. We're going to try to take away the pain part. The gain part, a subset of successful applications in the last years that we and I mean a lot of people around me as well have been applying these methods too. Density functional theory, non-relativistic and relativistic flavors, scattering of optical potentials, the emulation of, I don't remember these, but quantum Monte Carlo of the deuteron, and time dynamics as Kyle presented. Now, where is the pain on all of this? Remember our example of the harmonic oscillator. My equations ended up looking like this, and if I decompress this Hamiltonian, that is a 2x2 matrix, because of the affine structure of my operator, I will get a set of numbers, a matrix 2x2, plus alpha times another matrix 2x2. And I have those 8 numbers, 6 if you say that they're going to be symmetric, and that is the only thing that I care. Each one of these numbers were done by projecting parts of this operator to obtain what are the numbers I need for you. Now let's look at all the pain that this has caused. In this case, it's easy. If I want to really go through and be more efficient in my emulator for STERM DFT,
I'm going to run into troubles, and we have been running into troubles with this because my Hamiltonian depends on densities and depends on densities in a very non-affine and non-linear way. To illustrate the example, imagine a modified harmonic oscillator that is some sort of torture Grosby-Dayes equation in where I have 5 particles. Those are the 5 wave functions that I have in here. Each one of them have their own equation, and they all interact through a coupling through some density rho, that is just the sum of their squares. And I'm putting this parameter sigma here to make it this extremely harder to emulate if you're trying to do this with projections. So if you do this vanilla way, it doesn't work, and I have spent many hours, many days, many weeks trying to make this work. We have some workarounds, but this is a problem. Another problem, the relativistic mean field work that we did with Jorge, Frederic, Al, and Edgar a long time ago. Things work well because in here everything was affine, but you have many non-linear terms. So whenever you talk with Galerkin and Galerkin make the projections in your equations, you ended up with huge equations to solve for your reduced coordinates. This is a folder that is showing all the equations that I passed to Kyle whenever we were doing this project for the different fields and wave functions. If you open the coefficients for the fields, this is how it looks, and it goes down. I don't know if you see this white line, is this whole thing equals 0. That is the first projection. And if you zoom in there, this is how it looks. So it's a bunch of numbers. These numbers came from these projections on your wave functions and operators times your unknown coefficients times your alphas, the parameters that you're controlling. This thing is able to calculate the DFT predictions in milliseconds. It's still incredibly fast, but this seems wasteful. So that to me was a stressful situation when I had to deal with this problem. The scattering part, we have an operator that is non-affine in my parameters, so I cannot do the projection. What do we do? That's okay. There's a technique, there are many techniques, but there's a technique that is called the empirical interpolation method. And what we are going to do is say, I'm going to grab my potential, and I'm going to apply the exact same idea that I was applying for my reduced basis and separate it into terms that only depend on the parameters times terms that only depend on X. And then you have to worry on how you're going to estimate those coefficients. There is a lot going on, so much that this is one of my favorite figures for the Rose paper that I did. I spent an entire weekend making this, and it just shows how intricate this ends up becoming because of the problem of the non-affinity of the potential. 2 more issues. So this is pain without gain, because we still don't have publications with these 2 ideas that I'm going to share, but still there has been a lot of pain. To some degree, we have been able to make it successful. The first one is, what if you just do not have a Hamiltonian or an operator? You're trying to apply these techniques to the experimental friends that Thomas was talking about. You want, for example, to emulate how to control the beam of Sekar to make it line its target better. They have, I'm not going to go into details, but in the simulations, they have these matrix that are some sort of transfer matrix that tells you, depending on the current that you're pointing through the magnet, how it's going to affect the transport of the beam through the matrix, through the magnet. If you were to put this thing in a singular value decomposition, the eigenvalues are going to decay exponentially, and you're going to be like, aha, I have good reduced coordinates for this system. I can write an equation that emulates my matrix as a function of a current in a very fast way. But how are you going to get the equations for those things if this is not an operator? You don't have an equation to play with. That is the first problem. Where is your operator? The second problem is, what if you want to use extended reduced coordinates? For example, for the harmonic oscillator, what if I not only want to modify the amplitudes, but I want to modify the width of the wave functions? That is a valid reduced coordinate. Actually, for the harmonic oscillator, you need only one because the wave function is just doing this. So with only one, or well, 2 times the amplitude, you're going to get away with the entire manifold. But you can't if you want to project. If you want to go in an even further machine learning type of route, and you want to use autoencoders to extract what are the important features out of your solution manifold, what do you do with them? Because you don't have an operator that you can project into these coordinates. So that is what has led for our group to try to push learning equations from data that shares a lot of overlap with the philosophy, but not the machine learning applications of the PMs. So the idea was, I grab again my harmonic oscillator, I have my projection operators, we call this vintage Galerkin, and Edgar made this nice meme that looks like a vintage wine bottle. So this is the equation that we were having, and we're going to say, no. I'm not going to obtain these numbers of these matrix to projections. I'm just going to learn them from data. I'm going to try to fit this in a fake Hamiltonian, as Patrick was explaining, in where I have some constant term and then some expansion, for example, in my coefficients alpha of the operator that I have. And we were calling this black box Galerkin because we like to put Galerkin on every different type of situation. Interestingly, if you were to only do this inspired by what you will get from the reduced basis method, you should stop at alpha alone, because that's what this equation looks like. But if you continue, you might actually get something that fits the eigenvalue better. And the reasoning behind this is because you could think that in this case, my basis is not changing with alpha, it's fixed. But I could allow a manifold tracking system in where I'm not trying to do a single fixed subspace, but a subspace that is moving. That is going to be moving with alpha. And if you allow this expansion to continue, to some degree, it's trying to learn what is happening to H, but also to phi 1 and phi 2, which in principle could depend on alpha. Okay, this is, I want to make the connection with the work that our friends have been doing, and I only have access to the very outdated paper. So if at some point you want me to put a different picture here, I'm more than happy to.
So who's this very elegant guy on the upper right?
That's
me before I got old.
Yeah, exactly. So I want to again stress it. We are not using these for machine learning applications, and I don't think it would have ever occurred to me to apply this method into something like classifying digits. So in that sense, it's a really creative and very different thing, what our friends are doing. Okay, a couple of results from these approaches, and I'm almost done. This is the STREAMLINE problem that we were playing with. And the important point from this plot is that we were able to actually make an emulator that is way better in terms of the cat plot. All of the other approaches that we were trying before were just not working. They were basically on top of the high fidelity software. Now, this is a very inefficient way of expanding your Hamiltonian. I will touch base on that at the end of the talk. For the emulation of Sekar, and I just put a picture of Thomas because of the nice things that he said about connecting with our experimental and accelerator friends. On this initial approach with Diogenes and Rucci, we were able to get to emulate the transport of the beam in a way that was around 3,000 times faster than COSI, which is the software that they're using for their problem. And what we did, again, was just learning the equations from the data. This is the work that we are doing with Los Alamos team, and I wanted to put their pictures in specific because I think it's the first time that I have them in my slides. Just showcasing another problem in where learning from the data, which is the green, the PMM approach, completely overrun the other two approaches. In particular, the RBM was having a lot of pain with noisy wave functions. So this is a way that you can overcome that because you're learning your equations and your degrees of freedom from the data. I want to highlight how amazing Casey has been in this entire process. He's an undergrad student that is working at Los Alamos, and it's just a treat to work with. The final approach that I want to highlight, we have been working, this work started with Amy, one of Jorge's grad students, and suddenly has evolved to involve a lot of people from many places, trying to emulate going from the equation of state in nuclear equation of state to properties of neutron stars. And people from Cosmic Explorer are very interested in getting these simulators, even though it's not a very high computational cost. But when you have to do it a million times, it's actually important to do. In here, one of our friends, Brendan Reed, what he's trying to do is say, I'm going to invert this mass versus radius curve, just flip it, and I'm going to write an emulator of the radius as a function of mass, and how this changes with parameters. Same idea, I'm going to construct a fake Hamiltonian, and his first attempt was to use a one-parameter equation of state and expand the Hamiltonian in this way, and that led to an emulator that was like, meh. But then, after talking with me on the phone, the recommendation was don't expand on alpha, but instead expand on predictors of alpha or features of alpha, some function that is already taking some of the heavy lifting of going from alpha to a more meaningful quantity that you're trying to track your dynamical equations with. In this case, it's the pressure. Instead of just expanding in the parameters of the equation of state, just compute your equation of state and tell the system the pressure at this density should be this, the pressure at this density should be this, and so forth. If you do that, you get an increase in accuracy of 2 orders of magnitude. So this is a way more efficient way of learning your dynamical equations from data. And that is basically what I meant. When the first time that we did this, we were not thinking in that way. And now the work that we're doing is expanding in functions of the 3 parameters instead of the 3 parameters themselves that have a more straightforward dynamics. By the way, that is exactly how ROSE works. For any of you that are into the details, and you can ask me later because I don't want to deal with this in detail here, but I'm just going to say the input parameters are alpha, and you see this line, they go like here. You calculate the potential at these locations, and that's it. Everything else just depends on this calculation, not on the parameters themselves, but on the potential evaluated on those parameters. Okay, this is my last 5-6 minutes. Edgar, my friend Edgar, that I highlight in every talk, I was having a talk with him some weeks ago about this entire stuff, and we started reading papers. And my final point is what is out there. How is the rest of the community have been dealing with this? So I started looking for papers, and then I sent him this in WhatsApp, and I said, Edgar, I want to have some Galerkin continuation bias. I sent him a screenshot of the paper that I was reading. There, now let's play the game. When was this paper published? And in this paper that is saying, to correct the behavior, blah, blah, they consist in adjusting the polynomial coefficients with define the POD Galerkin system by solving a maximization problem. They're doing the exact same thing. They're learning the equations from data. This paper was published in 2005. So I was like, okay, I'm using black box Galerkin just to joke with my friends, but I'm not putting it anywhere because there is a lot of work that has been done ever since. And I'm putting a lot of things in here, many of which resonate with either the ideas that I have been having, the ideas that I have been discussing with Edgar, and even including the things that we didn't thought about, but when we read it's like, that is a very, very neat thing to try. This is not to overwhelm you. I'm going to come back to why I am putting all this here in a second, but I wanted to share it with you that there is a lot of things that we can learn, like a lot. I want to highlight my two favorite people doing these things, Nathan Cox and Stephen Brunton. Did I miss the? You got it right. Okay, fantastic. They have amazing videos and resources, and you see in here what they're doing is exactly what we are suggesting. We have to build ways of discovering good coordinates, in this case to autoencoder, and then discover models on how these reduced coordinates are evolving as you change parameters and time and what. So that is my share of surprise in the last week.
So for all those literatures, have you checked in ChatGPT today now?
I asked ChatGPT at some point, and it pointed to some keywords that then as a human, I look in Google Scholar and it helped.
So robots are taking our jobs.
Yeah. Okay, so questions and challenges. This is a personal perspective. I'm going to include Edgar and Kyle and people that are around me, but I'm not an expert on this, so this is what is in my head. You don't have to take this as prescriptive. The first question that I think we need to address is what is out there. How are we going to make a good feeling of what problems, what tools people have developed that we could just import directly to our problems in nuclear physics? And the way that I see it, is a bunch of awesome stuff that we have been able to do in the last years, but everything in here except this part, because we're using PMMs as it was prescribed by Patrick, Dean, and friends, everything else is using technology from modular reduction from 2004. Nothing else is newer than that. There's nothing wrong with using old technology. This is abstract from a paper that has nothing to do with this collaboration, but I'm just showing it. We are dealing with collinear models, and what we're using to deal with collinear models is principal component analysis, which one of the oldest citations that I can find is 1936. This technology, even though it's almost 100 years old, is perfect for the problem that I have at hand. So there is no shame in using it. Nevertheless, for many of the pains that I have had in the last years, it would have been very nice to have known all of these other techniques that could have been useful for that beyond the 2004. No.
Just as an anecdote, also in nuclear physics, there's all the work on, say, unitary pole approximation, lowering separable approximations for nuclear potentials that also predates all of this, but it's very similar ideas.
I need a map. I don't know about that. I would love to have a big map in where I can put that where it fits and how it connects to other things.
So Pablo, what is this journal? Psychometrica?
I have no idea.
There's no way that's it.
Yeah. I just asked ChatGPT what is a good reference for PCA, and it gave me.
It comes from actually psychologists who are interested in IQ.
Oh,
And
okay.
so how do you measure intelligence from testing? And so then the idea was there's a one-dimensional variable called IQ that actually explains most of the variability of test scores. That's where it comes.
Fantastic. Thank you so much, Sam. Okay, I'm running out of time. So my final things. I'm making a list of questions that I think is important to discuss during these 2 days and later in the future. What's out there? The second, why does this work? So for things like the harmonic oscillator, I can have an idea, perhaps for this type of system. For this one, I will expect that it will work. For machine learning and the things that Patrick showed, no idea. I have no intuition on why that worked there. Nevertheless, for these physics systems, my thinking is that if you have the right tool for the right job, you don't need that much data to feed it. My analogy is imagine that you have 3 points that follow a linear trend. You can fit a line, that has two parameters, and you will not be that much surprised if you were to then extrapolate and see, my thing is actually working very well. What I think is happening in this case is either you have system that looks like Hamiltonian matrices, or you can think that when you're tracking an eigenvalue, you're solving a determinant, but that is also the roots of the characteristic polynomial. So if your problem, you can track it somehow that it came from a high dimensional thing that looked like the roots of an equation. And you see that many of the things that I write as f of stop equals 0, that are to some degree roots of an equation, you will think that there should be a lower dimensional representation of the same form with smaller amount of parameters that will have this property. Yet, and that is my next question, I do not have any intuition on what to think when these things are going to break. When we were doing principal component analysis and regular RBMs, this is an example in where if you apply the RBM, it immediately breaks. It's the infinite square well. Your solutions are very localized functions. If anybody comes and tells me I want to do RBMs to solve this problem, I will say, no, the singular value is okay, not exponentially. This is a bad idea. I have that intuition. In here, you present to me a problem. Let's try to use PMMs to emulate the stock market. Will that work?
Of course it will.
But maybe yes, but I need that intuition. Otherwise, I'm going to always be like on my tiptoes, not knowing if it's something that is going to work well or not. I'm going to highlight these very nice pictures that I don't have time to discuss, made by Casey, which is trying to find the error of PMMs emulating high dimensional matrices. And the crazy thing is that these are very few data. So Patrick was using a lot of data to train his models. These are like 5 or 6 points. And the region in where the error is almost 0 forms these very cool, almost dancing-like figures. I want to understand that. We have some ideas, but not something that I can actually use. Final things, I promise. 1 more minute. What do we do from here? Now, my intuition tells me that something to work out will be to sit down and read a lot of what is out there to apply, to learn the equations from data. I don't have time, and nobody has time. So how do we move from here on? Last time that we were in a similar situation, we started the RBM Journal Club, and many of you will be able to see yourself in here. I don't think we all have time to do that anymore, but at least something that we could do in the Streamline meetings, and I'm going to propose this, we could have a folder with papers. I already have that, and everybody can contribute, and we can decide once a meeting, somebody reads one of these papers and make a summary. And that way we at least start looking what exactly is out there. I already started using the Ascension forum, and we can use that for communicating. I'm going to try my best to read, so if you want to join me in this journey, I will be more than happy to have friends. These are my conclusions again. I really want to move in a direction where we can streamline this process so everybody in nuclear physics can use these technologies to do it for the experiment. That's why we're after. I really like what I saw on the PMM talk, because that is the features that we need on these things. It's something that is very easy to just grab it and use it. I still have my reservations that I need to have intuition on when things are going to break. I believe that that is going to be the key, and I think we need to read. And with that, I'm going to take my collaborators, everybody else around, keep my slides, and now we have time for questions. Thank you.
All right. Thank you, Pablo. Wonderful talk, wonderful talk. Yeah, go ahead.
I want to understand better this idea of learning equations from data. So what exactly does it mean? So if I'm going back to the days of Tycho Brahe, and I gave you a lot of data on planetary motion, are you telling me that you can extract Newton's law of gravitation?
Yes, yes. Yes, you can. Yes. It's done by my people.
More than says yes. What I have, he probably has in mind something way more fancy or elaborate than what I'm thinking. When I say that, it's something like, if I were to do my Galerkin projections, I know what type of model I will get. I don't want to paint these numbers by that because I cannot for many reasons. Inspire on these type of things and extend it in any creative way that we think makes sense. Can I estimate these numbers from the data without doing a Galerkin projection? If I can, that I think is going to, I'm going to say the word again, streamline the process from anybody in this room or outside saying, my computer takes too long to do this. Can you help me build a reducer the model? And it will take maybe a couple of weeks in doing it, not 2 years, like what it took to make rows, or a year, what it took to make the relativity. That is it. Does this make sense, Jorge?
It makes sense, but I'm not more interested in.
Oh, yeah.
So what is the minimum set that we need to provide as nuclear data to get, for example, universal density?
That's a very good question.
Yeah.
That is the type of question that I would like to.
There is the same. These are my in
Well, this is something maybe we can discuss later more. Yeah.
I mean, connecting to what Farge asked, I mean, yeah, okay, maybe Lance Newton equation, but maybe Einstein ones, why not? And maybe 10,000 is an equation. How can one discriminate the simplest equation that can explain data?
So I think there are many types of answers to that. Do I have that? Yes. There are many possible answers to that. One thing that I like is anything that tries to promote sparsity. So I went over this extremely quickly, but the idea of what is happening here is you have a system that finds the reduced coordinates. That is the first time, the first part. Now you have these three numbers. Now you want to see how these numbers evolve. One way, which is what these folks are doing, is say, propose. I'm looking for how these numbers change in time because they're talking about dynamical systems. So I want an equation that looks three numbers prime, their derivative with respect to time, equal a function of functions of those numbers. So in here, they have a library of different combinations that you could have, and they try to minimize a loss function in a way that is promoting sparsity, meaning most of these things need to be zero. I don't want to have a combination of crazy stuff with cancellations, but rather very few active components. This is a way, this is not the only way. Does it make sense?
Yeah.
Now, this is just a follow-up to project. In this thing, if you go online, there's a guy called Miles Brandner and has several YouTube videos on with examples like taking all the astronomical data and then extract, let's say, Newton's gravitational law. There's several papers on that, and also fantastic TED talks by the same person. But obviously, as you said, I mean, for the specific case, you would have to think on how to, what kind of data would be relevant. But it's a pretty nice planned map.
I'm going to put it in the resources on the things that I
Okay.
Yes.
I don't even know what people have.
I should have made my talk about the solar system.
He's a high energy physicist, right? Kyle Cranmer?
Okay.
Yeah. Okay. Nuwa.
Hi, this is an open-ended question actually. So how would you contrast the empirical interpolation method with your fake Hamiltonian method or the parametric matrix models? How would you comment on that?
So I have this framework. It has a very well intuition on what my degrees of freedom from my potential are going to be. I'm going to expand this in reduced coordinates, and then I need a way to find those reduced coordinates for new values of parameters, and they are built through this process. Now, the difference, exactly. The difference is that when I did it with rows, I still was doing all of these projectors, so I was constrained on obtaining only these type of equations. I had a way of doing that, so it's a prescribed way. Just do these projections, group your terms in this way, and you will get a solution. If you were to do it by data, the idea will be to find this expansion. You see, the system that I'm solving in here in rows is small matrix, coefficients, unknown coefficients equals this a vector that also depends on the parameters. So the idea will be to have a matrix that I didn't compute these numbers by myself, but rather I learned those numbers that depends not on the optical potential parameters, but on the drivers, the predictors, the features that will be the potential evaluated at those locations, and then find a loss function, make a fake Hamiltonian that maps from those predictors to your actual coefficients that you're after, minimize that thing. And what would you get? I haven't done this. Because I don't have time, but I have the idea, and once I realize that the two things are the same, in principle, you should obtain something that is at least as good as rows, because you're minimizing, so it could find a better solution. But it will be much easier than doing these things. If you have the data, if you can only solve your problem 3 times, maybe this is not the way, but if in this case I can solve it 50 times, I could constrain these things from the actual solutions and information on how the operators do. Does that make sense? No?
I understand.
We can also discuss in detail later with the questions.
Okay. All right, let's thank Pablo once again. Have a coffee break and we'll return at 3:30. Beautiful.
Thank you so much. I am totally impressed. Really? Thank you. I really like it.
Too much going on. That's the point of the talk.